Chapter 13, Section 1, Bioenergetics in Thermodynamics. Your metabolism, yes, as I said at the introduction of this chapter, is all about the making and the breaking of things. Take big things, break them down into little things, take little things, make them into big things. But to do that, well, that's work. And to do work, you need energy. Okay, we got to get energy somewhere. Turns out, during that breaking down, that catabolic, you're going to get some energy out of those molecules. How much, what form, things like that, well, depends on what it is you ingested. We refer to this as energy transduction. Taking energy in one form, turning it into another. Taking in an excited electron, transferring it to an intermediate, that electron then pumping hydrogens across the membrane so that you get the flowing of hydrogens, causing an enzyme to spin, ATP synthase, making of ATP. So what was an excited electron is now energy caught in the phosphate-phosphate bond of A triphosphate. Energy transduction. Well, hopefully you remember back to your intro cell and molecular that, or hopefully they also talk about in cell biology, you have two laws, two rules that the universe has to function under. First, what is referred to as the first law of thermodynamics. Okay, it's called the principle of the conservation of energy. Energy cannot be created, cannot be destroyed. Okay? Energy does not come from nothing. Poof, there it is. Energy just does not disappear. Poof, there it goes. It could be changed from one form to another. Photonic energy becomes chemical energy, photosynthesis. Excited electron becomes chemical energy, oxidative phosphorylation. You go through and you strip off that third phosphate off of ATP and you put it onto an enzyme, activating that enzyme. You've just gone from chemical to chemical. The energy wasn't created, the energy wasn't destroyed. It was just taken from one form and turned to another. All of this occurs under the second law of thermodynamics. As you read here from the textbook, second law of thermodynamics says the universe always tends towards increasing disorder. What does that mean? What do we care about that? Well, basically what that states for us in a biological setting is that every time we operate under the first law of thermodynamics, excited electron to chemical energy to chemical energy, we take and we transform energy from one form to another, we're going to lose a little. Or if we do a really big change, we're going to lose a lot. You're losing a little bit of energy every time in your cells right now. Every time there is a reaction, a change in the form of energy, you're losing a little bit of energy in the form of heat, thermal energy. Got to remember, you're 98.6 degrees Fahrenheit, 37 degrees Celsius. Where did you think that internal temperature came from? It's the billions of chemical reactions in the trillions of your cells that's occurring on a daily basis. Every time that third phosphate gets stripped off of one, transferred to another. Every time an excited electron pumps a hydrogen, that hydrogen flows back, causing ATP to be synthesized by ATP synthase. All of these different things occurring, little bits of energy are lost. Well, turns out all that little bits of energy adds up. 37 degrees Celsius, 98.6 degrees Fahrenheit, thermal energy. What about this whole universe thing? Well, it turns out you heat up the universe an infinitesimal amount. Granted, as that thermal energy radiates away from you, it dissipates basically into the background noise. But yeah, there you go. When you look at this idea of systems and their surroundings, you'll see in the textbooks they refer to a reacting system. This is all the matter, chemical, physical processes that are occurring in either a closed or an open system. You're an open system, okay? You're constantly taking in stuff, gases, liquids, food. You're constantly expelling stuff, gases, liquids. You're pooing. Closed system's more of a theoretical. That means you take everything, you put it into a canister, you seal the canister, done. Whatever was in there stays in there. Nothing comes in, nothing comes out. Can't have a biological entity that works that way. Even our autotrophs have to take in carbon dioxide, have to give off oxygen or sulfur dioxide or some form of gases. Take in things, give off, waste products. The universe is basically a collection of these reacting systems and the surroundings. You do impact your surroundings. Your surroundings do impact you. Changes in the temperature, how much thermal energy is around you, will impact you. Too wet, too dry. How much light, real light, LED lights, things like that can impact you. But when you step it down and you look at the subcellular, what's happening subcellularly? Let's get away from the big picture looking at stuff. Let's narrow it down. Remember, hopefully, from Chemistry 421, Biochemistry, Selmalek, and other bio courses, this idea of free energy. Okay, how much energy is there in a system? This idea of G, how much energy is there, based on not only what reactants, products are present, what's the temperature, how much entropy, things like that. We call that the delta G. Now, delta G is counterintuitive. We always want to think that positive, high numbers are best for things. Well, actuality, when it comes to delta G, it's the opposite. The more negative, the smaller the number, the better it is for a reaction. Because these delta G's that are negative, and the more negative it is, the better, these are going to be reactions that are exergonic. Now, for you who are chemistry-minded watching this, think exothermic, okay? Same thing. An exothermic reaction that you've seen in the chemistry lab means you mix a couple of things together and the reaction heats up all on its own. Well, that heating up is the fact that that reaction, whether it's an organic or inorganic reaction, turns out that reaction is releasing energy. It's exergonic. Those reactions that you had to heat up, had to put on a hot plate and stir, keep it going, or at least to get it to go. Means by putting it on a hot plate, you had to add in heat, thermal energy. You had to add in energy, so they were endothermic. Or, from a biological mindset, they are endergonic. So the more positive the delta G, the more endergonic it is. The more energy has to be put into it for that reaction to occur. Now, to know if things are going to be exergonic, endergonic, we need to know also how much heat is going to be there in that system. Here's that exothermic, that endothermic that I was talking about. Delta G had to do with the energy. Delta H, well, is that energy going to be released as heat, or is it going to take heat? going to take some heat to get it to go. And again, the more negative, the more exothermic. The more positive, the more endothermic. And there's a price to be paid for everything. Entropy. Entropy is the disorder in the universe. How much disorder, how much energy, whether it's going to be the delta H, the delta G, whatever, how much of that energy is going to be lost. 98.6 degrees Fahrenheit, 37 degrees Celsius. You're going to lose some. And there's a lot of other constants and a lot of other things that are involved in this whole, thermodynamics beyond just the few constant things that we were just talking about. Delta G's, delta H, delta S, temperature measured in Kelvin, bring in Avogadro's number, 6.022 times 10 to the negative, or sorry, not 10 to the negative, 10 to the 23rd. Gas constants, things like that can also come into play when you're trying to actually discuss the thermodynamics, not only in a singular reaction, but in the open system of a cell, or maybe just in the cytoplasm or an organelle. That's a little hard for us to think about, and that's a little bit outside of our scope, because what we're really going to be focusing on is the delta G. Delta G equals the change in heat, delta H, minus T, temperature Kelvin, delta S, change in entropy. The more negative, the more spontaneous the delta G is, the more spontaneous the reaction is. The greater the chance the reaction is going to go just on its own. No outside help is required. As I said, when it comes to living cells, all living cells, not just us, not just mammals, but reptiles, birds, fish, plants, even microbes, bacteria, all operate under the second law of thermodynamics. It's just, the smaller you get, the less energy you're going to be losing because, well, you also have less energy at stake. And our friend, Keq, the equilibrium constant. Keq also comes into play here. Don't worry. I know you're sitting there thinking, oh my God, he's going to make us do calculations. No, I'm a biologist. We don't do calculations. Calculations are for chemists. But think about it. If you remember Keq, concentration of C, D, which are the products, C plus, of our reaction, A plus B gives us C plus D, substrates, products, beginning, ending. What you end with divided by what you began with. Uppercase letters, this is what the molecules are. Lowercase, how many of them? Because remember, you got to have a balanced equation. A number of A, B number of B, C number of C, D number of D. So C to the C, D to the D, divided by A to the A, B to the B. And if you notice here, there's a typo. They did B to the D, should be B to the B. Oh my God, you pay such big bucks for a book, you expect them to get it right. So when you're talking about these standard transform constants, delta G prime naught, K prime EQ, okay? These, if you remember, this is the delta G of a reaction that is going to be more theoretical because it is at a specific pressure, specific this, specific, you're pretty much not going to find in a biological setting. But it's the textbook, perfect conditions. Same with K prime EQ. So we can go through and we can start getting rid of the delta S. We can get rid of delta H. Because remember, it's going to be a certain temperature, certain pressures, and natural log of the balanced equation. Everything's at a equilibrium. Not biological, okay? Nowhere in any of your cells is there an equilibrium, because equilibrium means, it's one thing maybe across a membrane, but even then our cells don't want that to happen. And if it's a chemical reaction in the cytoplasm or in one of your organelles, if you hit equilibrium, nothing moves forward. So any type of, enzymatic pathway gets stuck. Yeah, cells don't like that. Living cells don't like that. But we could talk about it. That as the equilibrium constant gets larger, the delta G gets more negative, and the inverse. So that we see that the chances of equilibrium not being there means that our delta G is going to be more negative. Maybe that means things can occur. Things will push forward at some point. We can also take it as a means when you're looking at a reaction and you're discussing the equilibrium constant and the delta G prime naught as a means of trying to determine whether things are going to move forward or reverse. Because you got to remember, A plus B yields C plus D. Well, even though that's talk about it in that direction, it can go backwards. C plus D can yield A plus B. When you look at the K prime equilibrium, the delta G prime naught, if it's negative, it's zero, it's positive, which direction is that reaction going to be pushed in? A plus B, 2C plus D. If it's delta G here is negative, but if the delta G prime naught is positive, C plus D gives you A plus B, the reverse. And we can look at how much energy during some of these reactions is going to be released. Whether you're talking as kilojoules or kilocalories. The hydrolysis of ATP to give you A diphosphate, negative 7.3 kilocalories per mole is the delta G prime naught. That's going to be our magical number, because a lot of students ask me, why is everything based on ATP? Well, right there. That's a delta G that you get to bring to the party. When you go through and you break down ethyl acetate to give yourself ethanol and acetate, look how much energy is released. So when you're looking at the delta G, that equation from a few slides ago, delta G equals delta H T plus delta S, that's very vague. Here, delta G equals delta G prime 0, not, this is under the perfect conditions, plus RT, natural log of, and this right here is another way of saying K prime EQ. So that you can sit there and now you're taking into account everything in the term, you're being highly specific of what is being measured. Again, don't worry. No, I'm not going to make you do the calculations. May ask you to sit there and talk about it, but I'm not going to make you do the calculations. The free energy is independent of what pathway. Turns out some of these chemical reactions you see in a cell occur in multiple places because they're involved in multiple, enzymatic pathways. So which enzymatic pathway has no change on what the free energy is there. A certain reaction, A plus B yields C plus D, whether it's in the mitochondria, it's in the cytoplasm, it's in ER, doesn't matter. Still going to have the same constants. Turns out enzymes don't change the constants. High delta G, low delta G, whether there's an enzyme there or not. Just we're going to see over the next few chapters, having the enzymes there just cleans things up. Things that are endergonic. Well, having an enzyme there that's going to take energy from an exergonic reaction and refocus it just helps things along. The delta G is still going to be positive in that endergonic reaction. It's just now things are controlled better. And we're going to see that this free energy, the delta G between reactions, is additive. Remember I just said there's, a lot of times there's going to be pathways. The pathway, A to B, B to C. Well, it turns out going from A to B gives up a lot of energy, but this B to C, well, that's endergonic. A to B is exergonic, B to C is endergonic. Oh, okay. High, very low negative delta G, very high positive delta G. Link them together. The energy from A to B will power the reaction of B to C. So we call this additive. You look at this overall A to C, you only just add up the delta G's between them. It's why so many reactions in our cell are based on ATP hydrolysis. The breaking of ATP to A diphosphate, an inorganic phosphate, coupling that to a reaction, an enzymatic reaction that has a high delta G, bringing in that negative 7.3 kilocalories per mole of energy. Woohoo! And if you really start bringing in stuff, it turns out the constant, equilibrium constants, where the delta G's are additive, the K constants are multiplicative. Delta G's you add, K's you multiply. Other than in a biochemistry course, I've never actually done this, looked at this, but the delta G's, using the delta G of one reaction to sit there and determine how much of the energy is going to be required for, and can it power a second or a third reaction, then that delta G's type of stuff I have done not only in class but in labs and things like that. So yeah, the K equilibrium constant one,